So, the last lecture we stopped in deriving the boundary conditions over the surface separating two dielectric medium. Now, we have derived the condition as for the electric potential distribution. So, that means, if we consider this is the interface between two dielectric mediums, say 1 and 2, and that is the superscript we denote. So, that means phi 1 and epsilon E 1 is the permittivity, and phi 2 epsilon E 2 epsilon E 2 are the dielectric permittivity, which may not be equal for this two medium. So, we have already derived this condition del phi 1 del x equal to del phi 2 del x across the interface. So, that means, this shows that the x component of electric field is continuous. Now, if I integrate this equation from a equilibrium position, say where phi 1 is 0 and or phi 1 is a constant and phi 2 is constant. So, one can write phi 1 equal to phi 2 on the interface. So, this shows that the electric potential is continuous on the interface. And one thing to note that the electric potential, it appears as a gradient in the equation. So, if we subtract or add some constant to the electric potential field, it is not going to make any alteration. So, the interface potential, the electric potential, we can write this electric potential is continuous across the interface. Now, the potential on the interface, if zeta is the potential on the interface, so one can write that phi 1 equal to zeta on the interface itself. So, normally the surface potential, this is called the surface potential, is also referred as the zeta potential. If we say zeta potential, so zeta potential refers to the surface potential. So, now, if the interface possesses a charge density, suppose the interface are having a charge density, say sigma s. If the interface have a constant, a surface charge density constant, need not be constant, it can surface charge density, it can vary along the surface sigma s. Now, we need to have a condition, and which will be different. This condition is not sufficient. So, now we derive a condition from the already derived Poisson equation for electric field, that means equal to rho e. So, we know that epsilon E, divergence of E equal to E is the electric field, is rho e. Now, let us construct a elementary surface or area. If we are considering this is a x axis, let us consider a two dimensional case, and normal is the along the y direction. So, we enclose the surface, a portion of our interest, by a control volume in 2 dimension. It is a control area ABCD, like this way if I draw, and let us call this is the this length is b and this length is say a. So, if I now integrate this equation over this area ABCD, an area across the interface, integrate on ABCD. So, what I get is, this is a area integration epsilon E divergence of E dA equal to rho E ABCD dA. Now, E is the electric field vector. So, let us call Ex, Ey are the 2 components for E. So, this integration can be written as integral over ABCD, the area epsilon E outside, Ex sorry, this is not the one, because this is a divergence of E is present. So, it is not just exactly Ex, it will be the gradient of Ex. So, we can write this way, integral over ABCD epsilon E del Ex dx plus del Ey dy dx dy integral over ABCD rho E dA. Now, it is for 2 dimension. Now, if I apply the Green's theorem, to convert this area integral on the along the surface or along the edges. So, we get a over this curve which is enclosing the area, which is a rectangle. We have taken a rectangular control volume. So, if I now apply the Green's theorem over here, so what I get is, and also please note that Ex equal to theorem, also note this, Ex equal to minus del phi del x, phi is the potential, and Ey equal to minus del phi del y. So, one can write these as what we can write is integral over ABCD. I can write as epsilon E, this is Ey dx minus Ey dx minus Ex dy equal to this integral ABCD. This is the area integral rho E dA. Okay. Now, this on the curve ABCD. Now, when I am on the curve on the line AB, for this case it is a rectangle. So, this can be written, now we express this one as del phi del y. So, on AB what you have is dx is 0, because we have drawn this ABCD like this way. So, on this line you have dx is 0, on this line you have dy is 0. So, all these things if we now take into account. So, what I can write is, this is minus epsilon a b epsilon e Ex dy Ex dy. No, this is Ex means here we have del phi del x. So, Okay, so this is dy plus integral over bc epsilon e. Here it will be del phi del y. So epsilon e del phi del y means the ey. So del phi del y bc. So it is increasing. So this is minus plus becomes dx plus, like this way you have CD and this will be opposite AD. So this is equal to ABCD rho E dA. Now AB here, if we have taken, so this is in the other direction, because this is the direction over which dA is dy is decreasing, because we are taking y vertical. So this becomes your so this will be a negative sign. So epsilon e del phi del x dy, and then this one about BC is positive. So this becomes negative. Already it is taken care. So this is BC epsilon e del phi del y dx and etc. CD and minus AD. Now we have taken this symmetrically, and this is the one can say this is the net charge density enclosed by this term as the net charge density enclosed by the area ABCD. So this, if I now, this is over AB. So if I now possibly I should write it's plus, because this is a decreasing direction. So if I now put the value of AB, and we assume that the ABCD is a elementary volume. So on the face, on the faces of ABCD, no change on phi, and phi is known and variation is neglected. So if we do little algebra, we get this one del phi 1 del y plus epsilon e 2 del phi 2 del y equal to the volume charge density. So this is by 1 by b. B is the one the horizontal length rho e dA. Now, so this is the volume charge density by B. Okay. So this is a condition for the electric field. Now this term epsilon E is referred as the electric displacement vector. So this electric displacement vector shows a jump across the interface, Now what we do is we assume that the control volume is contracting to a single line. So that means let we have taken let this B A tending to 0. So that means this line AD is collapsing on the line BC. So let ABCD is shrink to a ABCD is shrink to the line on the interface, to the line by considering A tends to, by considering A tends to 0, A tends to 0. So what I get is epsilon E del phi 1 del y, this is 1. This is the permittivity of the other medium, the medium on the upper side of the interface, and this is epsilon E 2 del phi 2 del y equal to 1 by b into say rho A. If I call the rho A is the charge density, area charge density, so this becomes the sigma s. Okay. So, where sigma s is the interface surface charge density, because this is divided by the portion we are considering. Okay. So, this is called the jump condition, and this is the electric displacement jump condition, which is electric displacement jump condition. Actually, this vector epsilon e is referred as the electric displacement vector. So, when you have a interface which is separating two dielectric media, epsilon of permittivity epsilon E1 and epsilon E2, so you get a the jump condition is governed by this way. Now, if epsilon E2 is many times less than the epsilon E1, that is the interface is perfectly dielectric, that is non-conducting. Or you can say non-conducting. So, in this case, what we can write is, then we have minus epsilon E1 del phi 1 del y equal to sigma s. We can drop the superscript or this superscript and subscript 1, because in that case we do not require to know about the below the interface, that means the region with superscript 2. So, one can drop the so the conditions for the liquid side of the interface can be written as whichever way one can write epsilon E1, we are dropping this one, equal to sigma s, where sigma s is the surface charge density of the rigid non-conducting interface. Rigid non-conducting interface. So, this is the way now we can express the condition if we know the interface surface charge density instead of the electric potential, have the condition as electric potential. So, there also we get the potential condition as 1 zeta if we have a conducting situation. So, for example, if we have a conducting situation, so in that case the interface is conducting. So, in that case we can say that the interface potential is constant on the interface, and we can write this as zeta. Now, So, if I now jot down the conditions more precise way, we can write this way. Thus, the boundary conditions on a perfectly dielectric, or you can say on a non-conducting interface, charged interface, we can write charged interface is one is u dot n equal to 0. Now, I can generalize the conditions whichever we have derived just now to the case for here we have taken the interface as parallel to x axis and y was the normal to the x axis. So, one can consider the same way any other coordinate system, and if I call n is the unit normal on the interface. So, one can write the no normal flow, that is the u dot n equal to 0 and del ni by del n plus z I f by r t ni del phi del n equal to 0. So, these are the two conditions due to the no normal flow and no ionic flux across the interface, and we have either this condition equal to sigma s if we have surface charge density is prescribed, or phi equal to zeta. So, this is the conditions when you have the non-conducting charged interface. So, this also phi equal to zeta is also valid if we know for even a conducting surface, if we know the for a conducting interface, electric potential phi is constant. So, this can be also be prescribed as zeta. Now, if the interface is such that it is separating to dielectric media, so in that case we have the continuity of the dielectric displacement vector and also the continuity of the electric potential. So, and so the interface or say suppose if I am considering a flow or phenomena in a over a dielectric solid, dielectric rigid body. So, these conditions can be expressed as derived before. So, that means for a interface or on a interface I should say. So, on an interface separating to dielectric media, so this condition is true if it is a rigid, the condition 1 holds. Condition 1, whichever we have described for the no normal flux and no penetration of ions, condition holds, as well as and along with the conditions for continuity of electric potential. And the condition for dielectric displacement vector for the electric displacement. In other words, we can write as on the interface you have phi 1 equal to phi 2 and minus epsilon E 1 del phi 1 del n plus epsilon E 2 del phi 2 del n equal to sigma s. So, if sigma s is 0, so this is just a continuity of the electric displacement vector. So, on a perfectly conducting surface, so what we can see is that the phi will be just a constant, that is, the electric potential will assume a constant value for a perfectly conducting surface. So, that is the way when you have a considered a two medium this is the dielectric medium 1 and 2. So, they are coupled. So, that means you need to find out the electric potential in the region 1, this is coupled with the electric potential in the region 2 through the conditions given by this manner. So, let us consider condition 3. So, now we will continue to the next lecture.